The story of the fighter jet begins long before jets themselves. It starts in the mud and trenches of the First World War, where aircraft were first used simply to see what the enemy was doing. But it wasn't long before pilots started taking potshots at each other with pistols and rifles. This was the birth of air-to-air combat. Soon, machine guns were bolted onto these fragile machines made of wood, fabric, and wire. The fighter aircraft was born. A perfect example of this early era is the Sopwith Camel. It was a British biplane, meaning it had two sets of wings, one stacked on top of the other. This design gave it fantastic agility. It could turn on a sixpence, which was a huge advantage in a swirling dogfight. The Camel was armed with two synchronized machine guns that fired forward through the propeller. This revolutionary idea allowed the pilot to aim the entire aircraft at the enemy. However, it was a tricky beast to fly, with its powerful rotary engine making it want to turn sharply. Then came the Second World War, and with it, a huge leap in technology. Aircraft designers moved away from biplanes to monoplanes. A shining example was the British Supermarine Spitfire. Its beautiful elliptical wings provided excellent lift and reduced drag, allowing it to outturn many opponents. Unlike the Camel's wooden frame, the Spitfire had all-metal construction and devastating firepower that could tear an enemy aircraft apart in seconds. The Spitfire became a symbol of defiance and a war-winning weapon, a true legend of the skies. The end of the Second World War saw the dawn of a new era, the jet age. Piston engines and propellers had reached their limits. The jet engine was the answer. It worked by sucking in air, compressing it, mixing it with fuel, and igniting it. The resulting blast of hot gas pushed the aircraft forward at incredible speeds. One of the first truly successful jet fighters was the American F-86 Sabre. It looked completely different from a Spitfire. Its wings were swept back, a crucial design innovation. These swept wings were the key to flying faster than ever before. Straight wings created too much drag at high speeds. By sweeping the wings back, designers could delay the onset of shock waves that form as an aircraft approaches the speed of sound. This allowed the F-86 Sabre to fly much closer to Mach 1 than any piston engine fighter could dream of. The whole shape was designed for speed. It had a sleek, streamlined fuselage and a bubble canopy that gave the pilot brilliant all-round view, vital in high-speed dogfights. The F-86 proved its worth in Korea, leading to the world's first jet-versus-jet dogfights against the Soviet-built MiG-15. Armed with 6 powerful .50 caliber machine guns, it was incredibly effective in the close-range combat that defined these early jet battles. The materials used had to change dramatically. The F-86 was built from high-strength aluminum alloys that could withstand near-sonic flight stresses and heat from air friction. The jet engine required even more exotic materials like titanium and special steel alloys to handle immense heat and pressure inside. The jet age wasn't just about new engines, it was about a revolution in materials science. Flying near the speed of sound was one thing, but flying faster than it was a completely different challenge. This was the supersonic revolution. The American F-4 Phantom II was one of the first fighters designed from the ground up to be a true supersonic workhorse. It was a monster of a jet, big, powerful, and incredibly fast. It could fly at more than twice the speed of sound, or Mach 2. Its design was all about raw power and speed. To achieve these incredible speeds, the F-4 needed immensely powerful engines. It had 2 of them, fitted with afterburners. An afterburner is like a boost system for a jet engine. It sprays raw fuel directly into hot exhaust gases, creating a massive increase in thrust. This allowed the Phantom to accelerate rapidly and climb like a rocket. But all this power came at a cost. It was a thirsty beast, guzzling fuel at an astonishing rate. Its design featured drooping wingtips and a downward-angled tailplane, quirky features needed to maintain stability at supersonic speeds. The F-4 represented a shift in thinking about air combat. Early versions relied entirely on air-to-air missiles, not even fitted with a cannon. This proved to be a major mistake during the Vietnam War. Pilots found themselves in close-range turning fights where missiles were often ineffective. Later versions had a cannon hastily added back in. This experience taught designers that even in an age of supersonic speeds and guided missiles, maneuverability still mattered. American pilots developed new tactics, using the Phantom's superior speed and power in hit-and-run attacks, diving on MiGs and escaping before they could get into turning fights. The Phantom proved that raw power alone wasn't enough. The next generation would need both brawn and brains. By the 1970s, it was clear that sheer speed and power were not enough. The next great leap forward would be in the brain of the aircraft, It's avionics. The F-16 Fighting Falcon is a perfect example of this new generation of fly-by-wire fighters. In older planes, controls were connected by cables and hydraulic pipes. In the F-16, there's no direct physical connection. The pilot's inputs go to a computer, which then decides how to move the control surfaces. The F-16 is designed to be inherently unstable. This sounds dangerous, but it makes the aircraft incredibly agile, wanting to change direction constantly. The flight computer works thousands of times per second to keep it stable, giving the F-16 phenomenal maneuverability and allowing breathtakingly tight turns impossible without computer assistance. The pilot's seat is even reclined to help them withstand the powerful G-forces created during these maneuvers. The F-16's brain includes a powerful radar system housed in the nose cone, allowing pilots to detect and track enemy aircraft from many miles away. Information is displayed on cockpit screens, giving the pilot clear battlefield awareness, a massive advantage in combat. Compared to the F-4 Phantom, the F-16 was much smaller and more versatile, a relatively low-cost, lightweight, multi-role fighter. It could perform many different jobs from air-to-air combat to ground attack missions. Its advanced avionics made it easy to switch between these roles. The pilot could use radar to find enemy planes one moment, then use a targeting pod to guide laser-guided bombs to ground targets the next. The F-16 proved that a fighter's effectiveness was no longer just about speed or guns, but about the power of its onboard computers. The next revolution in air combat was perhaps the most dramatic of all: the development of stealth technology. What if you could build a fighter that enemy radar couldn't see? That would be the ultimate advantage. The F-22 Raptor perfected this concept for air-to-air fighters, designed to be virtually invisible to enemy radar systems. Achieving stealth involves two main things: the shape of the aircraft and the materials it's made from. The F-22 has flat surfaces and sharp angles designed to deflect radar waves away. There are no right angles on the aircraft's exterior, as these are perfect radar reflectors. Even the engines are buried deep inside the fuselage. The F-22 is coated in special top-secret radar-absorbent material, or RAM. This acts like a sponge for radar waves, absorbing their energy instead of reflecting it. The combination gives the F-22 a radar cross-section reportedly as small as a marble. On enemy radar, this huge fighter can appear to be the size of a small bird, or not show up at all. This stealth capability completely changes the rules of air combat. An F-22 pilot can fly into enemy airspace, detect and track enemy aircraft, and launch missiles without the enemy ever knowing they're there. It's the ultimate ambush. The F-22 can choose when and where to fight, giving it a huge tactical advantage. It combines stealth with incredible performance. It can fly at supersonic speeds without using afterburners, a capability known as supercruise. And it's extremely maneuverable, making it a lethal dogfighter if it ever needs to be. The F-22 represents the pinnacle of air superiority fighter design, combining stealth, speed, and agility in one revolutionary package. It changed the game forever, setting the standard for fifth-generation fighters. We stand today on the cusp of another new era in air combat, defined by data, networks, and even greater stealth. The F-35 Lightning II is the embodiment of this new reality. It's often described not just as a fighter jet, but as a flying sensor and information hub. Its true strength lies in gathering vast amounts of information and sharing it with other forces. It processes information and shares it with forces on the ground, at sea, and in the air. It's the quarterback of the digital battlefield. The F-35 has the most advanced suite of sensors ever fitted to a fighter jet, all fused together by a powerful central computer. This gives the pilot unprecedented 360-degree battlefield view displayed on a revolutionary helmet-mounted display. The pilot can literally look through the floor of the aircraft and see the ground below. With all relevant data overlaid on their vision, it's a level of situational awareness that pilots of the F-16 or F-4 could only have dreamed of. This information-sharing ability makes the F-35 a game-changer. It can detect a threat and silently pass targeting data to another aircraft or even a warship. The F-35 never has to fire a shot or give away its position. This network-centric approach means the whole is far greater than the sum of its parts. Looking to the future, the next generation of fighters will likely be optionally manned, meaning they can fly with or without a pilot on board. They will almost certainly control swarms of smaller, unmanned, loyal wingman drones. Artificial intelligence will play a huge role helping pilots manage immense information flow. New weapons like hypersonic missiles and directed energy weapons, yes, we're talking about lasers, will become commonplace. The journey from the Sopwith Camel's simple machine guns to the networked, data-driven combat of tomorrow is a testament to a century of incredible innovation.